Okay, welcome to class, everybody. So, real quick, we'll say a few words about the midterm. The scores are posted. The scores that are posted on Canvas are after curving, right? Every exam that I do in this class, I will bring the average up to 80%, right? Now, how did this class do versus the 6 or 7 years that I've taught this class? It's always about the same. The first midterm is always the lowest. The average is always in the high 40s, low 50s, and this was no different, right? So I bring the average up to 80%. The standard deviation, right? The standard deviation, if you remember what that is. Somebody remind me what a standard deviation means? What's that mean? We always talk about it like it's an error. If your data was a Gaussian curve, right, then you can take your data off of the center point and you can split it up into these standard deviations. And one standard deviation to either side is something like 34.1% of the total amount. So data never looks exactly like a Gaussian. This one actually looks more like one than some years. But what that really means is this is 80%, then 68% of the classroom, so 68% of you guys were within, 70 and 90 essentially, right, after the post curve. So don't be too worried about that. That said, what if you did really badly? Should you be panicking? Should you be dropping the class, withdrawing? I don't think so, and here's why. So in this class, I introduced something called a scaled approach to midterms. I don't drop a midterm because it's too important to just drop one, but I do allow students to make improvements and to account for that. So here's what I do. You're going to have 3 midterms in this class, 1, 2, and 3. And what I do is I take your worst performance on a midterm, any of the 3, and I make it worth 1/4 of the points that it would normally be worth. I take your best one and I make it worth 1.75, right? Way more points than it should be worth. So this is the effect it has. Let's say that Clark Kent takes the class, gets a 55, and then he hits the class average, an 80, which will always be the class average on these midterms, and then he gets an 85, right? So with the scaling, his score will come out to be an 80. It almost drops that low one, right? That as opposed to a 73 if we did without scaling. So a net improvement of 7.5 points. And you can see kind of different scores, what it would look like. Okay? So test this out for yourself. If you want to come and meet with me because you're freaking out about the class, we can say, all right, how well do you have to do on the next midterms? What is realistically your grade going to look like in the class? But as you can see, even if you totally bomb a midterm, you can really expect big improvements if you do well in your later scores. Okay? Like this person got 50, 50, and a 90, and it pulled it all the way up to a 73 with the scaling. So it really encourages you to dig down deep and just look past if you had a bad test and focus on the next ones and do better. Okay? Are there questions about the midterm? Yeah. The improvement number is just the difference between if we didn't scale it, 73, and if you did scale it. That's the improvement. I'm just saying that's how much of a benefit this will give you, and that it's not the same across the board. It's not like I give everybody, like, here's just 5%. It's based off of how much improvement you can do in a later exam. Make sense? Yeah, Chase?
And more generally, are the midterms, they're compartmentalized, right? So
that's right.
Yeah.
The difference is the final exam, which does cover everything. But the following midterms, yeah, it's just like now. We've been covering 3 chapters roughly per exam. We'll continue to do about the same. And so we can't cover previous material extensively. We might draw briefly on a concept, but it won't be the main thing I'm testing on because we don't have time. Okay, any questions about the midterm? You can pick them up anytime in my office. You can pick up your old homeworks if you haven't gotten them yet. Homework 3 will be back from grading probably by next class, so you can pick up all 3 if you wanted, along with your midterm. Everything good? Any questions about this? Okay, let's keep going then. So we are going to enter into a new chapter today, which is always a favorite. Typically, in the first couple chapters, which are chemistry heavy, the mechanical engineers in the course are like, meh. And then we get into failure and mechanical properties, and we see much more excitement. And this is your jam, so maybe apropos to be talking about failure after the first midterm, but we'll be talking about failure today, right? So let's talk about our learning objectives. For today, we're going to differentiate between ductile and brittle fracture. We're going to use something called fractography, which is really just looking at the surfaces of these things after they break to differentiate or predict. We're going to talk about stress concentrators and how they lead to failure. We'll introduce this idea of the stress intensity factor and fracture toughness. One of the more useful things we'll cover in this class is fracture toughness. And if we have time, we'll even get into the Griffith fracture toughness equation. So The book is decent in this. The third edition that was the oldest version of the book that the bookstore would buy, they wouldn't actually buy anything older because they, for whatever reason, they wouldn't. It skips some stuff. They actually skip some of the great derivations that I think are useful on this as well as Weibel modulus. So I've added some readings in the Canvas. You can check them out if you want to read about the derivations of stuff outside of just my notes. They might be useful, they might not, okay? But they're there. Okay, so maybe before we dive into this, let's do a demo. So we have some bananas that are about to give their life for science. So I need some volunteers. So Emma, come on up. Garrett, come on up. So you're going to need some safety glasses. Okay, so first off, Garrett and Emma are going to do an experiment for us. The experiment is this. We've got bananas, which are all from the same batch. They all look pretty similar. We're going to assume that they're roughly apples to apples, right? Banana. And we're going to do two things. We're going to have them break them. I'm going to have you break them in half, but don't do it yet, because we're going to do it two different ways. Garrett, you're going to bend it really slowly, at a slow, what we call strain rate. You're going to deform it at a slow rate. And Emma, you're going to try and break it as fast as you can, like a nunchuck, like break it right in half, okay? Okay, go ahead. Garrett, you had one job. One job. Slowly. Don't bend it fast. Okay, so what's happening? If we take a look at this one, right, fractography is looking at the surface. What can you say about the severed banana surface here? It's a shear fracture, right? What can you say about this one? It is not a shear. There's lots of plastic deformation. I know you guys have heard of this before. Elastic versus plastic. We'll talk a lot more about it in this class. This is brittle. It looks like a brittle fracture as opposed to ductile. No, that's you, man. That's all you. You can eat that. That's you. There you go. Okay? So that's an example of ductile versus brittle fracture. Go ahead, take a seat. All right, I need two more brave volunteers. Come on down, Isaac. Another brave volunteer. You're going to have to remind me your name. Riley, come on down. Okay, this time we're going to compare what Garrett did, which is a slow deformation, but we're going to do a difference. This time we have our ceramic knife, because we're not barbarians. Remember? Yttria stabilized zirconia, transformation toughened. Notice the tip is broken. They're still relatively brittle. My kid still broke this and broke the tip off of it, right? By dropping it. So this time we're going to do the same thing in terms of slow deformation, but I'm going to introduce a pre-crack, right? I cut maybe a quarter of the way through it, okay? So Isaac, slow as you will. You get really slow if you want. Go ahead and deform that. So what is it about, he went basically as slow, I think, as Garrett was going, but there, what does the fracture surface look like? It looks like a brittle fracture happened, okay? It looks like brittle fracture. That's you, Isaac. That's all yours. All right. Riley, you get the best job of all.
Oh, fantastic.
You get this frozen banana that's been chilling in liquid nitrogen, and you get the hammer of Thor that my student made for me. He forged this out of an old, car chassis. He reforged it into a hammer, which is the best thing anyone's ever done for me. You're going to put these gloves on. This whole first row is going to goggle so as to not get banana sharded. All right, you guys are in the splash zone. Anybody in the back? Feeling good? Okay. Oh, you got a pair. All right. Okay. Go ahead and just give it hell. That was so disappointing. It didn't even explode. Put that on the floor and smash it. Once more for good measure. But no, don't break any tiles. There we go. There it is. Okay, thank you. You can have that. Just don't freeze your fingers.
Thank you.
Okay. Or your tongue. Don't stick your tongue on that. Okay. What's the point of this demo? The point of this demo, apart from being awesome and leaving smoldering, smoking chunks of banana everywhere, is that ostensibly all of these bananas were basically the same thing when we started. they all were the same material, very slight differences in composition and microstructure. You would expect them to behave pretty much the same. And yet we saw, by varying a couple factors, pretty dramatic differences, right? In one hand, you saw relatively brittle, it made a nice fracture. In one hand, you saw extremely brittle, it exploded into banana shards everywhere. We saw really heavily plastic deformed. And think of the things that we can change. We can change what? What can we change? Temperature, clearly, of the material. And what else? The stress is like the pressure, right? The amount of stress that you apply. What's that?
Surface energy?
The surface energy. These might be the same. Frozen versus not frozen definitely is a difference. Yeah.
Like the point of breaking?
Yeah. We introduced a flaw on the surface, which is the worst place to have a flaw. And we'll talk about why in this chapter. So you can have flaws, you can have different stresses, you can have different strain rates. So the rate at which you apply that stress, all of these things can dramatically change how these things fracture and fail. Okay? So in this chapter, we're going to learn about some of these things. Okay? All right. So what is failure? Typically, in an engineering sense, failure is undesirable. Sometimes it is desired. Can you think of an example? When do we want things to fail? Carlos.
In climbing and ice climbing, they have some of the equipment designed to fail and break when it takes a lot of force, so that it doesn't take the full force. Because if the full force hits an ice screw, it breaks the ice that's stopping your fall. But if the device breaks and lets you down, it takes some of that energy out of the fall.
That's cool. I did not know that. I've been ice climbing. I didn't know that. That's very cool. In the back. Yeah. So by my simple definition, I said failure is a separation of a body into two or more pieces. So crumple doesn't quite fit that, but let's count it. That's still a type of failure when things crumple, and sometimes we want them to crumple as opposed to fracture because it's going to absorb a lot of energy. So your neck doesn't when you get whiplash, right, in the car. I don't know your name. What? Jordan.
Ceramic plates, like ballistic plates.
What type of plates?
Ballistic plates, like body armor, ceramic.
Yeah, the way that those break, they're almost always used in conjunction with other materials. So you have a brittle and a not brittle material working together, and you get a composite, right? Any mixture of two materials is a composite with better properties overall. Yeah.
They're like safety glass cars.
Yeah, the way that those are meant to break, just like that. They, instead of shattering and exploding all over you, there's a polymer holding them together so you don't get shards of glass in your eye. Yeah.
Packaging materials, you want to be able to open it.
Yeah, maybe you don't want it to be the strongest thing on the planet, because the most aggravating thing on the planet is when you're trying to open a pair of shears and you need another pair of shears to open it. Safety valves, right? In some of these pressure containers, you have a shear valve so you don't build up so much internal pressure that it becomes a bomb. Instead, a little valve shears at a very defined pressure, right? All sorts of things. But typically, failure is not something that we want. Unless you're designing for it specifically, generally speaking, we don't want it. And so, if it is going to happen, what this chapter is hopefully going to give us is at least be able to understand how to predict it, so that if we have it happening, we can mitigate that, see it coming, take it out of service, whatever it may needs to be. Okay? Fracture is going to involve two processes. If it's fracture, meaning it separates, you have to have crack formation and then crack propagation. Sometimes those happen almost instantaneously. When he smacked the banana like a hammer Thor, you saw crack formation and propagation basically instantaneously. Whereas when I pre-sliced it, they were very separate events, right? Crack propagation happened very separately. Or in other words, they can be spontaneous or non-spontaneous, right? Ductile fracture is characterized by this sort of non-spontaneous crack growth. You see it slowly happening under an applied force. Whereas brittle means it's very spontaneous. It happens. It's not like we can't see it happening. With a fast enough camera, we can. But it happens spontaneously without you applying additional force. After it initiates, it just keeps going. Okay? So, when you look at these surfaces, you'll see lots of different types. If you took a bar and you just pulled them, the book has these sort of diagrams. If this was your starting material, you can get the banana that was like a nice flat. You can get a very deformed banana. You can get what's called cup and cone behavior, which we'll cover in a few chapters. And you can see that. It really does form like a cup and a cone, right, behavior versus flat. Fractography is really useful because many of you might become engineers for some company where they're going to say, help us figure out what went wrong, right? Maybe you're making iPhones, and they come in and a customer says it won't turn on anymore. Hopefully that's not because of fracture. It's something else. But if it is fracture, you could always take that device, maybe section it, look at it, maybe look at the fracture surface as it is, and try and figure out what's going on. if you looked at it under a microscope and you saw the two following images, one of the hallmarks of brittle versus ductile fracture is the same thing we saw in the banana at a macro scale. If it's a really ductile material, ductile's over here, you'll see lots of deformation regions where the crack sort of meandered around portions of it, highs and lows, whereas a brittle material, it looks kind of mirror, right? Like very flat and glossy like that. The reason being, we'll get to in a minute, has to do with how the crack propagates, okay? In ceramics, you see very specific sort of defects. Ceramics almost always, at the point where the fracture occurred, right here, you can see this piece of glass they had, right where it happened, if you zoom in and look at that, you'll almost always see the region where the flaw was. There's very often a flaw at the surface of these materials. Not always, but often. We'll talk about why. The flaw, maybe this was like a little pore, or maybe a dust particle or an eyelash or something got in there when you made this thing. You'll see this mirror region, which has very few features to it at all. You'll see a hackle region. Sorry, mist and hackle. I mixed those two up. This is the mist region followed by a hackle. And this is kind of what we're looking at. See, that's our flaw. Very low. It's hard to see it in this image, but that's pretty much mirror here. And then there's sort of this extended out region. And if you go far enough out, you'll see all these big sort of cracks pointing towards the origin, right? So if you have a sample of something that broke, one of the very first things you ought to do is take a look at it. Look at that fracture surface and follow the lines. Let the lines sort of guide your eye, and you might see the cause of the failure right there. Maybe it was a nick on the surface that then turned into a crack that grew. Maybe it was some sort of other phase or a pore or something. But it's very common to be able to see these. It's easier to see them in brittle materials than in ductile materials. We'll show you what it looks like in ductile materials a little bit later. Okay? Okay, we're going to just introduce the very basics of fracture mechanics. Those of you that are mechanical engineers will take whole courses on this likely. We're just going to be the main ideas. And the big problem that scientists were trying to figure out when they started studying fracture mechanics is that if you calculate the cohesive energy holding atoms together, right? So the bond between Amelia and Garrett here is some number, right? They're bonded because they're atoms in some proximity to each other. And so to separate them, we could go back to our force versus energy diagrams, and we could figure out the force required to pull it away, right? In other words, the energy, right, over some distance. Force over distance is the energy, right? And that amount of force turns out to be humongous, right? Way, way bigger than what we see in reality. In reality, we can clamp onto the sample and pull it apart, and it starts to deform at way lower stresses, okay? Or it'll break at way lower stresses. So scientists were sort of puzzled, like, is our inner atomic potential model wrong? Like, what are we doing wrong that we're getting this so backwards, okay? So they realized that something must be happening. We're talking about 10 to 1,000 times lower, okay? So this guy in 1920, Griffith, who was the PhD advisor of my PhD advisor's PhD advisor. That amazing? I find that amazing. Anyways, he served in the Royal Air Force, World War II, amazing guy. 1920, he comes up with Griffith's fracture theory. Well, he starts the process. It took a while to figure it out. And he essentially said, okay, why are things breaking at a way lower stress? They must have something in them that's locally intensifying the stress. Okay, so let's say you got a pore, right? Make it sort of an ellipsoid, and the shape matters here. But let's assume that it has some sort of shape, and it has a distance from end to end, which we're going to call 2a. Why do they call it 2a? Because the thing that matters, as we'll learn in a minute, is the half crack length. If it was cut in half, how long would it be? 1a. But there's two of those, so we call it 2a. And he was the first one to sort of suggest that, well, maybe in the vicinity of these flaws in your material, the stress that you think you're applying to this thing actually gets magnified. And it's the highest right at the tip of that crack, which would be a reason for that crack to slowly extend and grow over time. Everybody follow me? Okay? So this is what the diagram looks like. If you apply some initial load, that's sigma naught. So in other words, if I clamp onto this thing and start pulling on it, that's the stress that I think I'm applying. That's the force divided by the cross-sectional area, which is some number, 50 megapascals, whatever, right? And in the vicinity of that crack, it's sort of exponential how it takes off until it reaches some maximum value at the tip. So the first thing I want you guys to write down is that the stress intensity factor, K is equal to the stress at some maximum point divided by the stress that you think that you're applying to it. Or in other words, the stress intensity factor, it's a multiplier. It multiplies the stress that you think you're applying And somewhere it's getting a lot more. And that's why all of a sudden things can fail at 10x, 1,000x lower, because you can get some major multiplication due to this stress intensity factor. Okay? Everybody with me? Any questions so far? All right, this was theory. And so then they started actually predicting what it ought to be. Since they knew the amount of force that it should take to pull atoms apart, they said, all right, we could actually maybe predict this since the crack does elongate based off of the size, the flaw in that. And they came up with some rudimentary expressions. They said, like, for example, the maximum stress right at the tip of that crack should be equal to your initial stress that you're applying multiplied by this term, which has your half crack length divided by rho t. That's the radius of curvature at the tip of that crack. Or in other words, if this is a tiny number, it gets more severe. If this is a big number, it gets less severe, right? So you have a nice sphere. That's sort of the best case scenario when it comes to cracks. If your crack is a sphere, best case scenario. If it's a hairline crack where it's a really small radius of curvature, you're going to get a bigger magnification, okay? So this was some of the first things that they were suggesting here. They simplified that, basically said, if the tip is small, you can leave out this portion. You leave out the 1. You can multiply it, and then you just get this. So all of a sudden, we're getting some useful approximations of stress. Then we've got the stress intensity factor where we take that ratio. Okay, so this was pretty useful. Let's jump over to our first clicker question. Oh, that's not a clicker question. Sorry. Well, that's coming later. Okay, so there's all sorts of different types of defects we can have. They can be on the surface. They can be at corners. Why are some worse than others? Okay, so turn to your neighbor and just postulate for a minute. Why do you think, I mentioned, for example, surface is worse than in the center. Why would a surface flaw be worse than one in the center? Turn to your neighbor and sort of discuss for a second. Okay, what do you guys think? Somebody give me your thoughts. No right answers yet because we haven't taught it, but what do you think? What do you think? What's going on?
Well, on a surface, it is often exposed to outside forces, whereas the inside of the material tends to not be.
Yeah. What sort of outside forces?
Just like anything that interacts with the material, whether that be like, I don't know if it's in a car, like a collision would interact with the surface before it interacts with the inside
Yeah.
of it.
Yeah. Have you taken statics yet?
I mean, it could.
So in statics, what would we say is happening here? Oh, all the hands go down like, no. All right, what do you think? What do you think?
The internal forces like shear and stuff, it doesn't matter so much on the outside. Those don't depend on the outside.
The bending moment, there it is maximized at the surface, typically. And that's not always the case. It's very often maximized at the surface. That's where you're going to have the largest bending moment, right, in your sample. So if we take this banana, right, I put a pre-crack in it, and I slowly start to bend it. Think what I'm doing is I'm bending it this way. I'm putting the top under tension or compression. Tension. The bottom's under compression. So if I did it the opposite, I would get different deformation than if I did it this way, right? Do we agree? Because there's a flaw right here, and I'm basically prying that flaw open, versus here, where the flaw is just getting smashed together. Do you agree that if I bend it this way, it's going to look more like the Garrett banana that got all over the place? And this will look more like, well, we saw this one. It's more brittle, right? So exactly right. The bending moment, it's typically cracks start from the outside, and they propagate through your material. They can start in the middle, right? You can build up internal pressure. You can do all sorts of things that cause the crack internally to start to grow. But that's not always the case, right? So surface flaws are a little bit worse, and they're much worse in brittle materials. And the reason why they're worse in brittle materials, any thoughts? Why is a crack worse in a brittle material? Science. Has to do with the spontaneity of a crack. Why do you think a brittle material has a spontaneous crack? Carlos?
Because non-brittle material is more elastic. It can take more deformation, whereas the brittle has less of that, so a defect will.
Yeah, you're on the right track. Think of what happens. Let's say we take this hairline crack for a minute, okay? You got a material. So that's your material from the outside. It's got a hairline crack. And we're going to pull on this thing, which is going to extend that crack. In a ductile material versus a brittle material, the brittle material is not able to deform. It can't tolerate plastic strain. There's no plastic strain. It's only elastic. So ceramics, you can't bend a plate. Once that crack starts, it just propagates. But in a metal, you can bend it, and what will that crack tip do you think? Will it get sharper as you bend it? It's going to blunt. It'll go from a hairline crack to something with a large radius of curvature. And in doing so, it lowers the local stress at the tip of that thing, right? And so if it can lower the stress, maybe it'll lower it enough to where it actually stops deforming, right? So that ability to plastically deform, Carlos is exactly right. Ceramics and other brittle materials, they can't deform. And so once it reaches a critical stress, it'll grow a little bit. And then why does it keep growing? Think about it in terms of energy. Let's go way back to free energy. We've got enthalpy and entropy. What do you think? Does the entropy change very much when you fracture a material? A little bit. It got more disordered. You've now got two halves, right? That's a pretty small change, right? What about enthalpy? Enthalpy, you took, like, let's imagine this is like our bulk material. If I put a new row in this material, just like there's this row right here, remember rows have dangling bonds. We don't like those. If I put a whole new row here, then we call that a surface energy, where there didn't used to be one. So that cost us energy. Why on earth would it ever do that? It has to have a driving force, right? And in a ceramic, when you're stressing it, the stress is that driving force, the stress that you apply to it, right? What the stress does, let's imagine I'm stretching all these students apart, I'm pulling them apart. They all would like to be some equilibrium bond distance. If I pull this whole thing apart, eventually they say, it's costing us so much energy for us to be stretched apart in terms of energy, we'd like to actually dissever, create a bunch of dangling bonds, even though that costs energy, but then all these other atoms can go back to being some equilibrium distance apart. That make sense? So the surface energy is lower, basically. In a ductile material, it's going to have a higher surface energy penalty. Okay, let's keep going. Griffith, what was really clever about what Griffith's fracture theory was is that he said, all right, anytime you make a material, these flaws are present. On the surface, in the bulk, you can't avoid them. You can statistically try and describe them, but if you make a big enough sample, it will have a flaw in it. Or in other words, if you have a small sample, it has some number of flaws in it, because they're typically large numbers. But not all flaws are equal. The one on the surface that I did to this thing is going to be a severe flaw. It's going to make it break really easily. But if I put a little nick, and I put it more on the edge, and I bend this thing just the same, then it's still likely to break in the middle for two reasons. One is that this is a bigger flaw, and the other is why? The bending moment increases to reaches my thumbs. Then it has a plateau of maximum bending moment, and so this little flaw is in a region of small bending moment. So it has two reasons why it's not going to break there. And so he started taking this stuff into account. He's like, okay, you've got lots of flaws. They're all over, statistically, randomly located in your material, maybe. Okay? And then he started saying that each one of these flaws has a stress maximum in the vicinity to it. And if you ever reach such a large local stress, sigma m, right? That's our maximum stress at the tip of that crack, that exceeds the cohesive stress of your material, that crack will start to grow. If it's a brittle material, it will just keep growing. If it's a ductile material, it will grow incrementally. Everybody with me? Any questions so far? Okay. So I'm going to skip some of the derivation here. He essentially did what I just talked about. He's equating elastic strain, which is bad. Putting your material under elastic strain puts it in a lower state. When you strain it, it's in a higher state. If you let it go, it will go back to, like if you're pulling it apart, it wants to go back to where it was, so it's going to shrink again automatically. That's why we call it elastic. It goes back, right? So when you pull on it, you're straining it, and it puts it in a higher energy state, which is undesirable, right? Now, if you were to break it along some surface, you create dangling bonds, which is also undesirable. And he basically equated these things, right? So, which was pretty clever. He equated these things and figured out a way to estimate the critical stress for ductile materials versus plastic materials. And he basically said, okay, it's going to have to do with things like your surface energy, gamma p, like the modulus of your material, the size of your flaw. He was the first to sort of introduce this ability to predict the stress at things which will break and tied it back to materials properties. Because before that, a big piece of steel and a small piece of steel, it was hard to figure out what was the relationship that was making these things behave, right? Because you had to take into account flaws and all this other stuff, okay? So in years after this, they continued to improve it, and they eventually introduced this idea of a critical strain release rate, which we won't cover in this class. And they introduced multiple fracture modes. They said if you break materials in different ways, they don't behave the same way. Like this is what we've been talking about in this class so far, basically, is pulling it straight apart. So your crack is essentially under pure tensile load. But what if it's under shear, right? That crack, what if you push it in and pull it out there so it's shearing along the direction of the crack versus shearing transverse to it? Those are very different types of loadings, right? Failure is going to behave differently because you've got different mechanisms that can take place, okay? In this class, we will only do the simplest model for fracture, which is mode 1, right? Mode 1 fracture. And even then, there's different ways to think about it. You could say, well, what if I've got a really thin sample. If you have a thin sample you're pulling apart, then we know that the stress everywhere is 0, right? And that the strain is non-zero. And then you've got plane strain, so if it's a really thick sample, the strain is it is equal to 0, and your stress has to be accounted for by knowing what something we'll call the Poisson's ratio in a moment. So we'll come back to these two scenarios in a couple chapters. So in other words, in this class, all we're going to learn how to solve is this one. If you take a fracture mechanics class in the future, which I hope you do, you'll learn all sorts of other scenarios. Right now, we're considering this. You've got a relatively big sample with a small flaw, right? That's the scenario that we're working with. And we're going to be pulling it under pure tension. Okay? Any questions? That's the assumption in this class. Finally, we get to Griffith's fracture equation. So what was awesome is they kept on thinking about this problem, and they finally said, what really matters is this stress intensity factor. The stress intensity factor was, remember, this multiplier that said, how much of a multiplier is there in the vicinity of the crack? And they introduced this equation. Right there. K, that's our stress intensity factor. You can rewrite it. We said before that the stress intensity factor is equal to sigma m divided by sigma naught. They also said, well, we can write this as y, a geometric factor, times the stress applied multiplied by pi times our half crack length, okay? And they realized that there is a critical value. There's a critical value for that stress intensity where if you go above it, the material will fail. Even materials that you would normally think of as ductile will fail. Like steel has a fracture toughness. It will still fail brittly, okay? So what is this y value? Y is a geometric parameter, which in this class, unless I say otherwise, the value that you use is 1.12. Right? Now, the actual value depends. It depends on a couple things, right? So, imagine this scenario right here. I'm going to zoom in on it. In this scenario, we have a surface flaw, which has a total crack length of A. If this was a internal flaw, like that, then the total distance would be 2 times A. But because it's at a surface, we only have half of the crack. So it's equal to A. Everybody follow me? Half of a crack, you get the half crack length. If it's a whole crack, you have to account for A plus A. This whole thing would be 2A. Okay? If A is small relative to the total sample width, then the A over W ratio approaches 0. Right? This is something like, I don't know, just looking at it, looks like maybe 1/10. So in this scenario, as it's drawn here, we're probably at maybe like right here, which is still basically 1.12. If you've got a material that has a really big crack relative to how big your sample is, like this, well, now look at that. We're basically at 3/4, so it's not even on this plot, right? But your geometric parameter starts to take off. So it's an assumption that oftentimes they teach in introductory courses that y is always 1.12, but in fact, it depends on your A over W. Yeah?
Are there any units associated with y?
Nope. Y is unitless geometric parameter. Okay? Y is unitless geometric parameter. Okay? Let me go back. So let's go back to this key concept. We're going to call it K, and now we're going to introduce 2 other subscripts to it. We're going to call it 1, Roman numeral 1, and then C equals Y, sigma, pi, A. Okay? Why do we do Roman numeral 1? because in this class we're talking about mode 1 fracture, which again means I'm taking this thing which has a flaw on the side and I'm pulling it straight up to fracture it, okay? So mode 1. And then C is the critical number. So this is really interesting. It's sort of like a seesaw. This equation, think of it like a seesaw. This is a material constant. You can look up for any material you want what its fracture toughness is, right? And if any combination of things on this right-hand side, when you plug them in, if it's larger than the left-hand side, then the stress locally, at least in some point of your sample, exceeds the critical stress intensity, and therefore it's going to fracture, right? So think about what this means. This is helpful because it brings together flaws and stress states, right? Because you could have a huge stress, right? Sigma is enormous, but a really small A and satisfy the condition. Maybe you did really good processing and you have very few flaws and they're really small. So A is really small. But still, a really large stress will cause it to fail. Or maybe it's the opposite. Maybe you think you're operating under a small stress, but A is ginormous. You've got some massive flaw. This allows you to calculate when things will fail under both of those scenarios because this is a materials property. It's a fundamental materials property. Okay? It depends on things like strain rate and temperature and all the stuff that we talked about, when we did our demo with the bananas. But those are things that people can experimentally determine, and then you should be able to use those as engineers to predict, okay, we can make things, but we can't get rid of flaws smaller than 1 millimeter. We just have to deal with the fact that we're going to have 1 millimeter flaws in our material. So if A is fixed, then you can design for a maximum stress to not break, which is pretty slick, right? Or other way around, let's say our application is going to have 100 MPa on it. No matter what we do, it's going to have at least 100 megapascals all the time. So what's the biggest flaw that we can tolerate, right? This is what they do on airplanes all the time. They know the stresses on an airplane, and so they say, okay, a flaw such and such of such and such size using this equation will cause it to fracture. So all we have to do is test our airplane regularly for flaws and see if any of them are bigger than our critical size. And this is what they do. That's what keeps airplanes in the air. That's amazing, right? That's amazing. Yeah, Chase?
Is there a standard unit for sigma?
Good question. In this class, we use the metric system, which is definitely the way to go, which means pascals is a unit of stress, right? That's a Newton divided by a meter squared. That might be the case. Is that right? Newton per meter squared should be a pascal. So when you hear me talk about megapascals or gigapascals, that's just a million pascals or a billion pascals. This is going to be in units of SI, so meters. If somebody tells you our crack is 3 microns long, what they're saying is it's 3 micrometers long, or 3 e to the negative 6 meters. This side of the equation has units, right? Unitless, units of stress, and then you've got square root of length. So what should the units of fracture toughness be? That should have the units of what? It should have units of pascals, root meters. And it does. If you look up tables, you'll find it given, unless they're horrible and giving you like imperial units or something, it'll be in pascal root meters or something, okay? So that the units cancel out. Any questions so far? So again, think of this as a seesaw, and then we'll do these quick questions. This side doesn't change. This depends on your material. You've got two things that you can engineer or design with as engineers. Abigail?
So you said that if the right side is greater, then it's more likely to break?
It will fracture.
Or it will?
It basically, it undergoes brittle fracture when this side is larger to that side. Now, there are materials where it'll start to grow and it will self-arrest. There's exceptions. We're going to use this equation for brittle fracture. That's what it was designed for, right? The derivation that you saw above in the previous slides, that was for brittle fracture. So that's what we're assuming right now. Okay? Okay. Yeah, we're not. We are not, or in other words, as your crack tip were different, technically we would want different scenarios here. I think that this is essentially assuming a sharp crack tip, and that it would be even worse, or better, sorry, if it was like a sphere. We're not going to take that into account in this class. In a fracture mechanics class, you would. And you would also take into account how Y changes based on how big the crack is. I think on the first homework, homework 4, which will be assigned Wednesday, and you'll have a whole week to get to it, so no rush. I'll post that probably later tonight. I do an example where, okay, this crack grows and it starts out really small, but as it grows, under some constant stress, it grows, but it doesn't reach the critical flaw size to break until it reaches this region where you have to account for the non-fixed number for y. Does that make sense? Or in other words, when you do this, you have to account for the instantaneous crack size. Okay? You can't assume that y equals 1.12 at all times right here. This thing no longer is equal to 1.12. It's changing. So as the crack grows a little bit, A is still smaller than the critical crack size, so it hasn't failed yet. But as A gets bigger and bigger, maybe y has to change. So I'll give you an example of calculating that on this week's homework. Yeah? Mina? No question? Just a stretch? Just a hearty stretch? Fair enough. Okay. Any questions on Griffith fracture toughness? This is Griffith fracture toughness. You have your fracture toughness. Under mode 1, there's a critical value. If any time this right-hand side exceeds it, we're going to assume that it fails in brittle materials. Okay? Should we keep going? Yeah.
Why do you increase the temperature so hard on glass?
One more time. So we will talk about that in 7 chapters. When we get to thermal properties, we'll talk about why glasses break when you change their temperatures. So just hold on to that thought. Okay, so these are just definitions. We've said that, again, fracture toughness, this awesome material property, remember, it depends on temperature. There's no reason to assume that a material is going to respond and have the same sort of resistance to fracture at room temperature as it will at high temperature. For one thing, at high temperature, it's going to be more ductile, and so it's probably going to have a higher fracture toughness. It'll be more likely to resist a fracture, right? Low temperature is going to be lower. It's going to be less likely. A high strain rate is going to be a lower fracture toughness. A low strain rate is going to be more tough, so it's going to have a higher fracture toughness, right? Okay, I'm going to skip this. Let's do one example, and then we can answer some questions. So let's assume this. Your material has a fracture toughness of 60 megapascal root meters. Okay? It has a yield stress of 1,515 megapascals. What's a yield stress? By definition, what does that mean, yield? Not break necessarily. It's when it means it's going to start to fail, right? It's going to start to maybe you're stressing something and you don't want it to permanently deform. It's the point at which permanent deformation starts, okay? So that's the yield strength of some material. And it says it's going to be subjected to a stress of the yield strength divided by 2, which is a common thing. We'll talk about whether this is a good idea or a bad idea soon. But engineers will look up a spec sheet and say, aluminum's got a yield strength of 300 MPa, so let's just never go above 100 MPa. Let's design it so that component never sees more than 150 or 100 MPa, right? A safety factor of 2 or 3. We'll talk about whether that's a good idea or a bad idea. But that's what they decide. Y is given as 1.12. And then it says, if we use an instrument to detect flaws, and it has a resolution of 3 millimeters. By the way, what are these instruments? Anybody used them before? Ultrasonic or X-ray? I'll have a sweet example. I'll do it next class. But yeah, ultrasonic or X-ray can basically look inside of a material and see where these flaws are at. But they have some limited resolution. They can't just go to arbitrary resolution. And this machine can only see as small as 3 millimeters. So the question I want you to answer is, will you be able to detect a critical internal flaw? So it's not a surface flaw. It's inside. Will you be able to see that flaw, or will this thing break and you'll have never seen it? So let's set this one up together. I think this is our clicker question. Okay? We're going to write Griffith's fracture equation first off. We're going to remind ourselves that K1C is equal to 60.4. That's megapascal root meters. That's going to be equal to Y times the applied stress multiplied by square root of pi times A. So how should we go about solving this? Somebody, what's the next thing we should do? Yeah, Carlos.
So we already have our Y.
Yep, Y is given.
Yield stress is.
We know what the yield stress is, and we know what the stress that they're going to actually apply, which is the yield stress divided by 2.
So we can solve for A, and if A is smaller than 3 millimeters, then we know that they won't be able to detect it.
Yeah, bingo. So square root of pi AC. So I'm going to write the subscript C next to A here. That's A sub C. That's our critical flaw length. So under this stress condition, which they've decided to use, we're going to solve for what the critical flaw size would be. If that is bigger than 3 millimeters, then we'll see it before it fails. If it's smaller, we'll never see it. This thing will just break. Question?
Would it be bigger than 1.5 millimeters? Because it's
Yeah, great question. So we said it's an internal flaw. So the total flaw size, which you can call X, right, this whole distance there, X equals 2A. And what we can see X, right? That's what we see with our tool. The tool doesn't tell us half crack size. It just says, I see a flaw in your material, and it's some dimension. So go ahead and tell me what you think. Are we going to be able to detect this or not? What's that? No, but she emailed me and said, oh, you can just email it to me. I'm like, oh, dang it. I want to see an example. So I might just send what you guys, if you can send me your poster, I might just send a variation of that. Because I don't know what they want to see. I think they want to see something closely aligned to their research, not just like a generic blue sky machine learning puzzle. Okay, get your answers in. Another 1 minute. Okay, get your answers in. We're going to close the poll. What do people think? People think, I'm guessing a split. No, mostly they think that yes, we'll see it. So how do we know? When I plug this in, I end up with something like 1.6 millimeters, about. 1.61 millimeters. But that's the half crack length, right? The total crack length is twice that, so 3.2. So X equals 3.2 millimeters. Or in other words, if we can see down to 3 millimeters, we would see that before this thing failed. Okay? So there's lots of types, homework questions like this. You want to see more examples that are worked out. Otherwise, that's what we've got today, and we'll pick up next time talking about More fracture.